Look at this experiment. Scientists fire a beam of photons into a device called a beam splitter, which sends a single photon into two possible paths. At the end of these paths, they place two detectors to check where the photon ends up. This setup is one of the best ways scientists have to make a single photon behave as if it is split into two paths. But here is the strange part. If scientists try to measure the photon on one path, the other path instantly disappears. The moment a measurement is made, the two paths collapse into one outcome, and the detector suddenly records a full photon on just one side. This effect is deeply connected to non-locality. It seems as if both paths of the photon know about each other, and choosing to measure one path immediately eliminates the other, even if the two paths are extremely far apart. This opens up some of the deepest questions about the nature of reality. Before we measure it, is a photon truly in two states at the same time?
Some of the puzzles in this experiment that the individual photon really presents you with?
Well, I think that at the end, the only thing I can do is once again invoke non-locality. That is to say, I think of the single photon wave packet as being split on the beam splitter. So now I have half a wave packet on the right and half of the wave packet on the left. But if I measure on the right, if I detect the photon on the right, instantaneously the other wave packet collapses to zero.
We usually assume that everything in the universe follows cause and effect, that events unfold in an orderly way, governed by clear and predictable laws. But quantum behavior challenges many of these long-held assumptions. It hints that something deeper may be operating beneath the surface of reality, something far beyond anything we can currently compute or fully understand. In this video, we'll explore how scientists have tried to explain this strange quantum behavior through new theories and experiments, and what these ideas reveal about the true nature of reality. As you'll see, every explanation leads to even more disturbing paradoxes, questions so profound that science still has no clear answers. When we think about quantum mechanics, the first question that hits us is, does reality really behave in such a strange and illogical way? Or is it just our lack of understanding? We are asking this because, at everyday scales, the universe behaves exactly as our classical theories predict. Planets, cars, apples, and machines follow clear, logical rules that we can measure and calculate. But when we go to the quantum world, the realm of electrons, photons, and atoms, our familiar rules fall apart. Here, particles behave so strangely that they force us to ask deeper questions. Is the universe fundamentally real in the way we think? Are our mathematical theories unable to capture the full truth? Is nature itself probabilistic, or is something hidden from us? This confusion comes from some blunders or surprises seen in quantum experiments, surprises that completely broke classical logic. You already know this. An electron around an atom does not have a definite position until it is measured. To describe this more precisely, scientists use the idea of a probability cloud, a region that shows where the electron is likely to be found. Sometimes this cloud is shown as a probability wave in a 2D form. In simple words, it represents how the chance of finding an electron changes as you move in a straight line away from the nucleus. For an electron in a hydrogen atom, the probability is low very close to the nucleus, becomes highest at a certain distance, and then decreases again as you move outward. This wave does not tell us where the electron actually is. It tells us the probability of finding it if we make a measurement. But here comes the big philosophical question. Is the probability wave just a mathematical tool, or is it describing something that actually exists in reality? Some scientists believe the wave itself is real, that before measurement, the electron truly exists in a spread-out state of possibilities. This is what upset Einstein. It led him to say, "Does the moon exist only when I look at it? God does not play dice." Einstein believed the universe must have definite properties even when unobserved. But over time, experiments showed that the quantum world really is stranger than he thought, and Einstein was wrong. But even after decades of research and countless experiments, some of the most important questions in quantum physics remain unsolved. Even today, we still don't know things like what actually causes the probability cloud to collapse into a single measured value? How does this collapse happen? Is it a real physical process, or is it simply an update to our knowledge? To answer these questions, scientists propose many different quantum interpretations. Each interpretation tries to explain: what is reality? Why do probabilities collapse? What does a measurement truly mean? But every interpretation also brings its own paradox, a deep puzzle we still cannot solve. Let's start with Copenhagen interpretation and the paradox it creates. According to this view, the probability wave is not a real physical thing. It is just a mathematical tool that tells us what we can expect to see when we make a measurement. In this interpretation, the electron does not exist in any definite position before we look at it. It has no exact place, no exact value, only probabilities. The collapse happens the moment we measure something. It's like nature chooses one possibility out of many and locks it in. Before measurement, the electron is everywhere it can be, but after measurement, it is suddenly in one specific place. For example, imagine rolling many dice at once, but you don't see their faces until you lift the cup. Before lifting the cup, the Copenhagen interpretation says the dice don't even have a number. Only when you look do they become a number. This interpretation treats reality as something that is not fully real until you observe it. That's why people sometimes summarize it as, the world is blurry until you look at it. Copenhagen is the oldest and most widely taught interpretation, but it has one huge problem: the measurement paradox, also called the observer paradox. The heart of this paradox is simple. It asks what exactly counts as a measurement. Who or what causes the wave function to collapse? One paradox is, if collapse happens when the detector measures it, then the detector is an observer. But detectors are just machines. Why should the universe care? Second, if collapse requires a human mind, then consciousness controls physics, which is deeply unscientific. And third, if collapse never happens until someone checks the detector, then the whole world is in an undefined state when unobserved. This makes reality feel dependent on observation, which many scientists find uncomfortable. According to this interpretation, the probability wave is completely real and it never collapses. Instead, every possible outcome actually happens, but in different branches of the universe. The Copenhagen interpretation says measurement collapses the wave function, but many worlds says there is no collapse ever. Instead, the probability wave continues evolving smoothly. Branching happens without any special rule for observers. Measurement is just another interaction of quantum systems with the universe. There is no privileged role for consciousness, no magical collapse happening on observation, no weird line between quantum and classical. So if an electron has a 30% chance to be here and 70% chance to be there, then the universe splits into two copies. In one universe, you find the electron here. In the other, you find it there. Both outcomes are real, just separated. Here's an example. When you flip a coin, according to many worlds, the universe splits into two every time. One where it is heads, one where it is tails. You only experience one version, but the other version also exists. Reality, according to this view, is a giant tree of splitting universes. Many worlds is elegant mathematically, but philosophically explosive, and this creates paradox. If every possible outcome happens in some branch of the universe, why do we experience only one outcome? Why do we feel like we live in a single stable world? In other words, if infinite versions of you exist, why do you never notice them? How do you even define you in such a universe? It also brings three other paradoxes. One is conservation of identity paradox. If every measurement splits you into multiple copies, which one is the real you? All of them? Or none of them? Second is Probability paradox. Quantum mechanics predicts probabilities 50% spin up, 50% spin down. But if all outcomes happen, what does probability even mean? Why do we always experience outcomes that follow probability laws? And the third paradox is the cosmic inflation paradox. According to the many worlds interpretation, the splitting of reality never stops. Even when you read this sentence, photons from your phone scatter, molecules in your eyes absorb light in different ways, neurons fire or don't fire. Each microscopic event causes branching. So the number of new universes created each second is far larger than the number of atoms in the observable universe. Where are all these universes stored? What are they made of? How do they not interact with each other? In this view, the probability wave is a real physical wave and the particle is also real. Quantum particles always have definite positions, definite states, and definite properties. Nothing is fuzzy, nothing is undefined. But there is also a second ingredient. Each particle is guided by a real pilot wave. Imagine the electron is a little boat and the pilot wave is the ocean beneath it. The boat always has a definite position, but the wave determines how it moves. This wave is not imaginary. It is physical, real, and fills the universe. There is no collapse. Measurement simply reveals where the particle was already located. The wave only guides it. It doesn't magically disappear. Reality in this view is completely real and deterministic. Everything has a cause and an effect, but the causes are hidden from us. Pilot wave theory solves the measurement problem, but introduces a huge new paradox. If particles always have definite trajectories, and the pilot wave instantly affects distant particles, how can this be consistent with relativity where nothing can travel faster than light? This is the non-local trajectory paradox. Also, pilot wave posits two layers of reality: the particle layer, what we see, and the wave layer, what controls everything. But the wave is invisible and unmeasurable. So how can we prove it exists? Are we inventing an invisible universe to explain a visible one? This makes some physicists uncomfortable. According to these interpretations, the probability wave is real, but it doesn't collapse because of observation. It collapses because of natural physical processes, as if the wave is unstable and eventually breaks down into a definite state. The probability wave lasts only while the system is tiny, isolated, and not disturbed. Larger systems collapse quickly. Any interaction with the environment or gravity can trigger collapse. Imagine a soap bubble. A small bubble can float for a while, but a big bubble pops quickly. Similarly, a small probability wave of an electron can stay uncertain longer, but a big wave of a macroscopic object collapses immediately. This is why we never see a chair or a football in multiple places at once. In this view, reality is not dependent on consciousness. Collapse is a built-in feature of nature. This interpretation of objective collapse avoids the observer problem but creates new paradox. What exactly forces collapse? If collapse happens spontaneously, what causes it? If collapse is triggered by gravity in macroscopic world, why does gravity decide what counts as too heavy? If collapse is triggered by size, what size is the magic cutoff? If collapse is random, what random mechanism controls it? Nature seems to have secret rules we can't see. According to relational quantum interpretation, the probability wave does not describe the electron itself, but describes the relationship between the electron and the observer. The electron can have a definite position relative to one observer, but not to another. For example, the electron may have no definite place relative to you, but it might have already interacted with another atom earlier. So for that atom, the electron's position is definite, but for you, it is not. Reality becomes something that depends on who is looking and what has interacted with what. The collapse happens only from the point of view of the observer who measured it. For another observer who has not yet looked, the collapse has not happened. There is no God's eye view, no universal master version of reality. Every observer has its own version of the quantum world. Reality becomes a network of relationships instead of a single universal truth. Now we reach the heart of the relational quantum paradox. Relational quantum interpretation says there is no single universal collapse of the probability wave. The collapse happens only from the point of view of the observer who interacts with the system. And here comes the paradox. According to this interpretation, different observers can disagree about whether collapse happened, which means there is no single shared reality. How can the universe function if reality is not the same for everyone? This breaks the classical idea that there is one truth about the world. This creates the no view from nowhere paradox. If all facts are relative to observers, then the universe has no single objective timeline, no single objective set of events, and no single objective history. The many worlds interpretation says that collapse never happens. Reality simply splits. The pilot wave interpretation says there is no superposition at all. A guiding wave directs the particle like a pilot. The relational interpretation says collapse does occur, but the outcome depends on who is asking the question. But cubism or quantum Bayesianism, which scientists believe the most unusual interpretations of quantum mechanics, says the wave function is not a property of the particle. It's a property of you, the observer. You can think of it like this. The wave function is your personal belief about what might happen. Superposition of a particle is just a way for you to express uncertainty about the outcome before you check. It is not the particle itself that is in many states. It is you who is unsure. And collapse of the wave function is not physical. Collapse happens in your mind when you update your beliefs after making a measurement. Nothing magical happens in the outside world. Everything happens inside your mind. Now we reach the paradox, one of the strangest in all of quantum philosophy. If every observer has their own wave function, if every collapse is a personal belief update, if every quantum outcome is a personal experience, then is there any shared reality at all? How can many observers live in one universe if each observer's quantum reality is uniquely personal? If reality is personal, why do all personal realities agree when observers communicate? Cubism says the universe is participatory. Observers shape outcomes through actions. When observers interact, their experiences become mutually consistent, but the deep question remains. If reality is personal, who or what glues our personal experiences into one common world? Consistent histories gives a totally different kind of answer. It says reality is not made of particles or waves. Reality is made of histories. You only ever see one history at a time, and many possible histories simply cannot be combined. This interpretation doesn't need observers, wave function collapse, or parallel universes. Instead, it says, the universe is like a storybook with many possible plot lines. But you are allowed to read only those stories that are self-consistent. Any story that creates contradictions is automatically forbidden. And the superposition of a particle means you have not yet chosen which history is valid for your questions. But the universe will only allow you to ask questions that belong to the same storyline. In this interpretation, there is no collapse at all. Instead, when you ask a question, you select one consistent set of histories. That selection eliminates all incompatible stories. Collapse is not physical, it's not mental, it's not even an update of belief unlike cubism. It is simply, you chose a context, and that context decides which histories are allowed. This interpretation leads to a deep and very strange paradox. It says different questions create completely different realities, and these realities cannot be combined or compared. But if reality depends entirely on which set of histories you choose, and different choices produce mutually exclusive versions of reality, then does reality even exist independently of the questions we ask? Or is reality manufactured by the context we choose? In this interpretation, the universe is like a library full of mutually incompatible books. You can pick one book at a time, but you're forbidden from mixing pages from different books. This is incredibly elegant mathematically, but philosophically shocking. The superdeterminism interpretation of quantum mechanics says something radical. It says you never truly make a free choice during a quantum experiment. The particle you measure, the setting you choose, the neurons firing in your brain, the movement of your fingers, even the vibrations in the air, all of them were already correlated through hidden variables going all the way back to the Big Bang. According to this view, there is no wave function that mysteriously collapses and no genuine quantum randomness. What we call superposition is not a real physical mixture of possibilities. It only reflects our ignorance of the hidden variables that already determine the outcome. So, when you measure a particle's position, superdeterminism says your decision to measure that property, the particle's value, the device settings, the final outcome were all fixed by deep, cosmic-level correlations long before the experiment started, long before you were even born. In this interpretation, what looks like a random collapse of a wave function is simply an unfolding of a predetermined result. This challenges one of the key assumptions of Bell's theorem. Bell assumed that experimenters can freely choose measurement settings, independent of the particle's hidden variables. Superdeterminism rejects that assumption completely. This interpretation creates one of the most shocking paradoxes in all of science. If every measurement choice is predetermined, then science itself might just be the universe watching itself unfold with no real freedom to test alternatives. It questions whether scientific inquiry is genuinely open or simply another predetermined chain of events. This is the heart of the forbidden freedom paradox. Superdeterminism preserves realism and determinism, but at the cost of free will, testability, and the foundations of science itself. Well, these are the major interpretations that try to explain the quantum world and its strange behavior. We've also seen the fascinating paradoxes that each interpretation creates. Now it's your turn. Which interpretation do you think actually describes reality? Share your thoughts in the comments below. Thanks for watching.